Hello students, in this module what I am going to do is to basically clarify some of the questions related to partial differentials and multivariable calculus that were raised in the forum, and I thought it's better to just clarify it via a brief video. So first thing that I would like to clarify is the conversion of the Laplacian into the cylindrical coordinates, polar coordinates. So remember we had this kind of question or this kind of a situation where we wanted to convert this to a partial differential equation or a partial differential expression in terms of r and theta, where x is r cosine theta and y equals r sine theta, right? This is what we were trying to do in the earlier video, probably part 2 of the partial differential module, right? So in that context, what we were trying to do was that we were trying to write down an expression for partial x of the function f in terms of the derivatives in terms of r and theta, because remember in this expression the original partial differential equations you have expressions or derivatives with respect to x and y. So first thing what we have to do is consider f as a function of r theta, and then you will get df is partial f partial r at constant theta dr plus partial f partial theta at constant r d theta. Now I am going to write df by dx, right, which is obviously at constant y, is partial f by partial r times partial r partial x at constant y plus partial f partial theta constant r partial theta partial x constant y, right? This is what we have to do. Now we need or we know the expressions for these, what is partial r partial x, what is partial theta partial x, from the fundamental expressions for so you know what is r is x squared plus y squared to the half, and theta is tan inverse y by x and so on. That means that you can find out what these derivatives are. When we did that, we obtained the following expression, which is nothing but we were able to get partial f by partial x at constant y is nothing but cosine theta partial f partial r cos theta, sorry, at constant theta minus sine theta upon r partial f by partial theta constant r. Okay. Now what is partial squared f by partial x squared? It is partial x operating on partial f partial x, which means all I have to do is, if I were to think of this like an operator, cos theta partial r at constant theta minus sine theta by r partial theta at constant r operating on f, okay, right? Now this is partial x, right? This is the operator partial x operating on f expressed in terms of r and theta coordinates. Now I want the second derivative. So what I have to do is to operate this once again, right, r operating on the same thing again, cos, I'm sorry, this should be cos theta partial by partial r at theta minus sine theta by r partial theta, right, operating on f. Sorry about this skewed writing. Now the key thing that I probably didn't explain very clearly in the previous module was that when you think of this, you should not think of it as you know, a minus b the whole squared and expand the operators, because these are not algebraic expressions alone. These are operators. So when this is operating on this is operating on cos theta and partial r. When this is operating on this is not just operating on partial f partial theta, it's also operating on sine theta by r. So you have to use chain rule. So that gives, if you do it carefully, that gives rise to additional expressions. Okay. So let's go to the next page and do this. So what we are going to do is to simply do this additional step of algebra more carefully. That is, what we have is, we are interested in partial squared f by partial x squared is nothing but cos theta partial r minus sin theta by r partial theta operating on cos theta partial f partial r minus sin theta by r partial f partial theta. Now, you have to operate this one by one. So, let us operate the first term. Let us operate this term on this term. You will get the following, which is, see, when I operate partial on cos theta, it's not going to give me anything because theta is independent of r. So, I can pull this out. So, cos squared theta partial r squared. Now, let me operate this on this. I will give minus. So, here I have to be careful. Here I have, this is a function of r and theta. So is this 1 over r is a function of r. While I can pull the sin theta out, I cannot pull the 1 over r out. So, I have to write cos theta sin theta. First, let me keep r constant. I am going to use chain rule by r partial squared f by partial r partial theta. Now, I am going to keep this constant. I am going to pull this out. So, minus cos theta, right, sin theta partial f partial theta. Now, I have to do d dr of 1 over r, which is minus 1 over r squared. Okay, this is the extra term that you get. Now, I will do the same thing for the second term. So, the second term is, so now first I have to treat theta as constant. So, I will get minus sin theta cos theta by r, right, partial squared f by partial r partial theta. Now, I will keep this constant and differentiate this. So, minus sin theta by r partial f partial r. Now, partial by partial theta of cos theta is minus sin theta. Okay. Now, I will have to do the same thing for this term. So, first I will get sin squared theta by r squared partial theta squared. Now, I will have to treat this. Okay. So, I will have to treat plus sin theta by r partial f partial theta. Now, r is constant because this is an derivative with respect to theta. So, I will get an r squared. Now, I get partial theta of sin theta, which is cosine theta. Now, we have to look at various terms. Okay. So, if you look at this term, this minus and minus will make this plus, and that is identical to this. So, this will become a plus, and this minus goes away, right, and then this term and this term are identical because this is sin theta cos theta by r squared partial f partial theta, same. So, this will give you 2 sin theta cos theta by r squared partial f partial theta. Okay, that is one thing. Now, the next thing that you will see is that these two terms are also identical. So, you will pick up a minus 2 cos theta sin theta by r partial squared f by partial r partial theta. So, we are done with, let me just cross out terms that we are done with. We are done with this term, 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 and we are left with only, let me just write it. So, this is partial squared f by partial x squared is cos squared theta partial r squared, okay, minus 2 cos theta sin theta by r partial squared f by partial r partial theta, right, and then you will get this term plus 2 sin theta cos theta by r squared partial f partial theta plus, then you will get sin squared theta by r squared partial theta squared. Now, let us check out all the terms that we have copied. So, we have done this, right, that is the first term. Now, we have done this, that is the last term, right, and I think we have pretty much written all the terms, right. So let's just see whether we missed something. We have not returned this term, right? We have not written this particular term yet. This has not been written. So we have to include this. This is nothing but plus, because there are two negative signs, sine squared theta by r squared partial f partial r. Okay, so if I clean up a little bit, this expression will now become, sorry about this, is cos squared theta partial squared partial r squared partial squared f, because I am operating it on f, right, plus sine squared theta by r squared partial f partial r minus sine 2 sine theta cos theta by r partial squared f by partial r partial theta plus 2 sine theta cos theta by r squared partial f partial theta finally, and then I'll get plus sine squared theta by r squared partial f partial. Hang on a second. Okay, so I have written this here. So let me erase this. So I've already included this term. Let me erase this and write the last term, which is sine squared theta by r squared partial squared by partial theta squared. Okay, so these are the various terms that are there in this expression. Similarly, you have to write partial squared f by partial y squared using the same procedure, and you will get sine squared theta partial squared f by partial r squared minus 2 sine theta cos theta by r squared partial f partial r, right, plus 2 sine theta cos theta by r partial squared f by partial r partial theta plus cos squared theta by r partial f partial r plus cos squared theta by r squared partial squared f by partial theta squared. Now, if you look at these two expressions, right, let's just first cancel out various common terms. This must be a theta. This cannot be an r. This must be a theta. I'm sorry. You can check your earlier notes. This has to be a theta. Okay. This has to be a theta. Now, let's strike off terms that are cancelling out, right? So this is minus 2 sine theta cos theta by r squared df d theta, so plus 2 sine theta. So this goes with this, cancels, right? Now, in the same way, this is minus 2 cos theta. Okay, so let's just write it here. Okay, let's just, this term is going to cancel out. This is minus 2 sine theta cos theta. This is going to cancel out with this. Okay. Now, similarly, this term is cancelling out with this term. Okay. Now, you look at this term and this term. They will give rise to a cos squared theta plus sine squared theta d squared f dr squared. Cos squared theta plus sine squared theta is 1. In the same way, if you look at this term and this term, I'm sorry if I have not written an f here, because this has to have an f, right? Okay. Now, if you look at this term and this term, again partial squared f by partial theta squared times 1 over r squared times cos squared theta plus sin squared theta. Cos squared theta plus sin squared theta is 1. Similarly, if I look at this term and then if I look at this term, again you will pick up a factor of sin squared theta plus cos squared theta by r, which will be 1. Okay. So, finally, what you will end up is, therefore, after all the simplifications, you will get partials. I am sorry about this, let me choose right. Partial y squared is nothing but, after all the simplification, you will get partial squared f by partial r squared plus 1 by r partial f partial r plus 1 by r squared partial squared f by partial theta squared. Okay. So, this is a very standard result for conversion of Laplacian from Cartesian to cylindrical polars, right. Now, there is one more question that was raised that is regarding the notation for the Taylor series of two variables. Okay. Let me just clarify that. The question was the following. The question was, if you had a function x, y, and if you want to write the nth, the Taylor series up to n terms. So, I wrote this as n is equal to 0 to infinity 1 over n factorial times delta x partial partial x times delta y partial partial y whole to the n operating on f of x y. Obviously, these are evaluated about the point about which you are expanding the Taylor series, right, writing down the Taylor series. Now, one thing that you should note is that these, let us say n is 2, right, you will have an operator of the type delta x partial partial x plus delta y partial partial y operating on itself. Now, if you operate on this on itself, you have to remember that this operator, this delta x is not operating on this d dx is not operating on dx. Similarly, this d dy is not operating on dy. So, that is the notation, okay, so that you can write it in a simple way, right. So, this was the question that was asked, that this is not agreeing with what I wrote 2 steps earlier. It will agree provided we agree not to operate these delta x's partial partial x on delta x and delta y and so on. So, this is just notation, there is nothing to worry about this, right. This so that you can write it in a simple manner. Now, the third question that was raised was with regard to the maxima and minima of a function of two variables. Okay. Now, after Taylor expanding and keeping terms up to second order, what I wrote was f of x y minus f of, okay, I will stop here.